time.
Now, on my schedule, which you've all got, the next guy, Chris Kelly, is a local boy from where I live. So, not local. I think I'm technically incorrect there. He is, he's going to introduce himself. This is from New Relic. He is going to talk, well, you've seen the story so far, and this is incredible. Normally, talks at conferences have no relationship to whatsoever to each other because they invite speakers, and the speakers at the last minute say, I want to talk about this. And the conference organizer just left with a big pile of rubbish that doesn't make any sense. These three talks make perfect sense with each other. We had Matt's talking about Ruby and how awesome it is. We had the next guy, who I don't think I want to say his name, because he got up on stage and said it's not very good at all. And now Chris is going to prove it, because Chris is actually going to show you the C code that I talked about. Please put your hands together for Chris Kelly. Thanks, sir.
Well, good morning. As we have talked about, well, so one of the colleagues that is here showed up yesterday or the day before, and ended up wanting to have lunch at like noon. Gets in, it's like, let's have some food. I'm like, you know, it's still breakfast, right? Because breakfast lasts until 1 o'clock, and I think that's kind of awesome. I'm really excited about that. Because I like to party until 5 in the morning and sleep. This is a lot like I was in Greece at Baruco, actually gave the same talk, and this is the last time I'm giving it, so you guys are that audience, I guess. And they party until 5 in the morning, you sleep in until noon. I'm liking this lifestyle, this whole American thing of like, let's get it into the office by 9, out by 5, kids in bed by 6. Seems terrible. So I'm really enjoying this. I've been here for a few days, and so I'm really excited to be here. This is one of the conferences I've been really excited to talk at, and the speaker lineup is just insane. I don't know how I found my way onto that speaker list, but I'm very privileged and thankful for that. So my name is Chris Kelly. On the internets, though, you can find me as Amateur Human. That's GitHub, Twitter, Gmail, wherever. I respond best on Twitter, so if you have questions or thoughts or you want to send some hate mail, send it to Twitter. Email, I'm less reliable on. I work for a little company called New Relic, and I want to say thanks to them for sending me here and letting me to do this, and that's really nice of them. So today is a story in 4 parts. We're talking about garbage collection. We're going to walk through the entire system from what happens when you do Foo.new down to the garbage collector. So you're going to look at a lot of C code and very little Ruby, and it is tradition in Ruby conferences, we're not actually going to look at Ruby. We're going to look at things like JavaScript or C or Haskell or Clojure. We talk about other languages in Ruby conferences for some reason. So the first start is for people that aren't familiar with garbage collection is at all. So we're going to kind of give you an introduction to that and find out what we're talking about. Next, we're going to look at how to navigate C Ruby and what's going on with that. And then we're going to talk about object creation. That's actually walking through a few hundred lines of C to see exactly how objects get created. And finally, we're going to end up at the garbage collector, because when you create objects, you need to get rid of them. And so we got to figure out how to do that. So what are we talking about? We're talking about MRI. We're not talking about JRuby. It has a different garbage collector. We're not talking about Rubinius. It has a different garbage collector. We're talking about MRI. We're talking about C Ruby. And that's all we're going to talk about. This isn't a general talk about garbage collectors, so we're not going to get into like all kinds of theoretic algorithms of different garbage collectors. We're going to talk about MRI's garbage collector, which you saw a little bit of a preview recently. And we're not going to look at tons of Ruby. Like I said, you got about 12 lines, and then after that, hopefully you can keep up. The goal of this, though, is to introduce you to how to navigate the C code so that you're not intimidated by it. There's a paper by Nari called Rare RGC Talks, and this is part of the problem with talking about GC and Ruby internals in general is a lot of the stuff is in Japanese. And we need to expose that into a broader audience so we can get more contributors. More contributors are better ideas, and we can spread that knowledge and we can share that burden, right? It shouldn't be upon 5 people to build Ruby simply because there might be a language barrier. And I was really inspired when I was doing some research for a New Relic project by Nari's paper of rare RGC talks. So I think that's really important. So I think there should be more GC talks or more talks about internals so that we can expose that and get people familiar with it and that they're not so intimidated by it. Because let me just do one raise of hands thing. I won't do another one. How many people have opened up a source file, a header file or C file in Ruby? Now, how many of you just immediately closed it because you're like, I have no idea what's going on? Right? That's the general consensus. You open it up because it's not just regular C. It's Ruby C. It's how the Ruby team, all the idioms that they use are in effect there, and you need to deal with that, and you have to learn how to read that Ruby C. So that's what we're going to talk about today. But first, the origins of this started when New Relic moved from 1.8 to 1.9 last year. Hopefully nobody is still on 1.8, but maybe you still are. So we track on how much garbage collection takes, and this was taking on average about 80 milliseconds for using New Relic. We switched over to 1.9, and we saw a bump to 42 milliseconds. And so that sparked an interest of, I'm privileged enough to get to do goofy things like do research projects like this, to find out why is there a big drop in garbage collection time between those two. So you end up saving 48% just by upgrading. Now, if you're caring about the performance and you're still on 1.8, you've got some screwed up priorities. 1.8 is end of life. Hopefully you don't have any production applications running on it. Make sure you do get to get upgraded and kind of get out of that end-of-life product. And also, garbage collection is very application-specific. So you're not going to always get the same sort of performance improvements that, say, New Relic got when we went from 1.8 to 1.9. But you can save some, so make sure you upgrade now. And 2.0 is even better, and we'll talk about that. So Ruby is all about objects, right? We know that. We learned that. We'll hear it probably a dozen times today and another dozen times tomorrow, which is awesome. Garbage collection is all about objects, too. So what is garbage collection? Well, as Vicent described, it's a two-headed monster. Ruby's MRI garbage collection is conservative. That means, and this is juxtaposed to precise, the conservative garbage collector doesn't know what's going on. It doesn't know what memory allocation is a pointer and which one's actually just memory. So anything can be cast as a pointer and then throw an error. So it has that problem. It's conservative. It's mark and sweep, so it has two phases. It has to traverse the entire object space, and then mark everything that is still available to it, and then sweep away the things that it didn't mark. And then stop the world. That means your code stops running while this process is going on. And that's really important, and that's where Ruby got a lot of its bad performance habits very early on. And I think this is an effect of, Matt's talked about it a little bit earlier, that Ruby was intended to somewhat replace Perl in Matt's life, right? Like he was doing a lot of scripting. These are very short-lived things. But so a mark and sweep algorithm, a very naive one, is very fine in a scripted sort of lifestyle. Objects never live long enough to matter. But what happens, though, when you run Rails, and Rails is a giant script, those objects stay in memory. Rails, your code gets put into memory and keeps getting marked over and over and over and never gets swept away. So there's massive amounts of time sitting, checking your code that it's never going to clear away out of memory. So Ruby, in its 1.8 days, when it was just a naive mark and sweep, was not intended for the Rails applications that ended up being run on it. And so I think there is some leeway we need to give it, right? That performance is bad, but it's not fair to say 1.8 and Ruby is a poor performer. We were trying too hard to use it. So, and since 1.8 to 1.9 and 2.0, now 2.1, we'll see that so much about the garbage collector is changing that it actually is sort of fitting the new world in which Ruby works and where it's often running Rails applications, or at very least long-running processes rather than these very small scripts. So let's look at some object space. Object space is a module inside of Ruby that allows you to traverse everything in Ruby, or anything in memory. So it looks a little like this. This is just a really basic Ruby script that I threw up. It doesn't have actually any functionality in it, so it's just initializing it and then counting the objects. So you can see on a real basic Ruby script, 14,000 objects get created. In a Rails application, just a really simple CRUD application, 280,000 objects get created on startup. That's a lot of time. And you're going to see that as we have to go through this process of object allocation over and over and over, we have to do that 280 times. You can kind of get a sense of where this performance characteristics come from. So let's start with creating a class. We're going to show you what's happening as we do these things. So we've got 478 class objects currently. We're going to go ahead and create a new one. We'll call it Foo. Foo's going to create two objects. It's a little confusing, right? So you've got the original class object, and then its meta class. So that creates two class objects. So then let's look at array. Let's create an array. It does exactly what you expect, increments it by 1. Let's fill it with 10,000 foo objects. Kind of does what you would expect. Then we're going to try to collect some garbage. Nothing happens. We haven't released any of that memory. It's still being used. Nothing special. And then we're going to go ahead and empty out that array, see what happens. So the memory hasn't been reallocated or hasn't been recollected yet. It's still in perceived to be in use. So we still have 10,000 objects. We run garbage collector again. That's going to trigger the event that causes that memory to be released. And now we're back down to 8. And then let's go ahead and get rid of our class that we created and collect again. And we're back down to where we started. That is what we're talking about. As we create a Rails application, as it boots up and it creates those 280,000 objects, it's going to do this over and over and over. It's going to run through these processes. So before we can talk about that process, though, we need to look at some C code on how to navigate C Ruby. What's really interesting, I think, though, is that there's a very idiomatic style. And hopefully after this talk, you will find that you feel very comfortable looking at the code because it actually reads a ton like Ruby. You can clearly tell this C was written by people that think like Ruby is written. And the same thing that Matt's talked about this morning. It's the language defines how you think. And you're going to see this C code is very much the same. So we're going to really be looking at 4 major files. This is just Ruby written in C. It's all in these headers and a couple C files. So first, we need to understand value. To understand value, this is a macro, and this macro is going to return a pointer most of the time. This is the very first trick that the core team uses to start getting performance characteristics. We end up getting either a pointer back from the memory, a pointer to the memory, or on very small objects, things like true, nil, false, we don't want to have to go get a memory reference and then go get the value of it. We actually just want to embed it directly. Because it's much smaller, and we spend too much time going back and forth to get true over and over and over and over again, how many times you use the value true. So by using this macro, this value macro, the developer doesn't have to care how it's stored, whether it's actually a memory object or if it's just one of these special values. You just call, I want the value back from this thing. If it's true, it gives you back true. If it doesn't, it gives you back the pointer. That's a neat trick, because you're abstracting away some of the legwork that as a C programmer you might have to kind of do all these if checks and statements, and you're hiding them behind these macros. So I think that's a really neat trick, and it comes into play often in a lot of the Ruby idioms. Additionally, you have all of these various types, right? These look very familiar to you. You've got structs for every kind of Ruby object. There's a C equivalent to them. Each of these objects is allocated differently, so they have to be kind of handled differently. And then, so let's look at what a basic object is. Our foo class is just, when we create them, it's just basic objects. So first, we have RBasic. That contains 2 components. It includes a flags table, and it includes the class pointers. Like, these are pointers. The flags include things like frozen, embedded, things like that, whether it's been marked for GC yet. That's where we store all of that information. And then the class is just a pointer to the class type it is. So this would be a pointer to foo, for example. So then in a regular object, we embed the RBasic. So then every object that gets created has this flags table and this class pointer. It also has things like the number of instance variables. You can see the instance variable table and things like that. So that's pretty basic. If you look at it like this, I think it starts to get a little bit more clear what kind of happens. So you use value to return the RObject. That's going to return the memory, the pointer. Then we're going to get RBasic inside of the RObject, and that's got our flags and our class again, and then our instance variable. So you can see how it lines up pretty well in the code. All right, so that's what this is the kind of visualization we're going to use most of the time. So what are macros? I've used the term macros a couple times. Macros are just code substitution. All that is you're abstracting away a whole series of checks that allow you to, it's all these if checks that happen. It's often sort of whether I want to get the value back or I want to get the pointer back. I don't want to have to think about that as a developer. Like, there's an interface that I can use, and in some case, macros allow me to do that and not have to worry about it. It's actually how much of the much more complex code is written such that you don't have to concern yourself. When you're writing a C library, or you're working in just a random chunk of Ruby, you don't end up having to care about how to get back the string. You just say, I want an R string, and bring it back to me. I first realized this in an article from Pat Shaughnessy, where he discovered that different lengths of strings have different performance characteristics. So strings over 23 characters take longer than strings under 23 characters. And that's because of this embedded element. So first, in a string, we have two components. We either have this struct, which is actually just the table with a pointer to the actual values. You saw some of that in Vicent's talk. Or we end up having this embedded value. So the string under 23 characters gets embedded directly, much like that true or false does. So it doesn't take two lookups in order to get the value back. And we create a lot of strings when we're using Ruby. So Pat discovered this, and this is where I really understood the value of things like macros, right? So at some point in time, this embedded system didn't exist. But over sort of performance analysis, and the core team discovers, like, hey, what if we embed this information directly? But then how do we get it back out? If it's sometimes in a register that we have to pull out, or if sometimes embedded inside of the memory object itself, how do we get it back out? Well, we use a macro to do that. So anytime I want to pull up a string, I use this RString pointer macro. And that's going to do a couple things. First, it's going to check to see if the embed flag is set inside of it, and or the VM itself has been set to not embed anything, because you can change that flag. In that case, you can return the array itself, you can return the macro, or you can return the value of the string itself, or if not, you can get the pointer through the heap. So I think this is a very interesting trick, because otherwise I'd have to spend most of my time writing things like this, compiled with a bunch of if statements all over the code in order to get a string back, and that's a lot of work. Instead, I can just use this RString pointer macro all the time to get back the things I need. So you'll see as we go through the 20 different methods or 20 different functions that go through to create objects, how many times macros will come back. And I think that's one of the areas that a lot of developers get choked up on, was macros are sort of a idiosyncratic thing that C supports, and not everybody has ever seen them, and so it's really important to understand the macro. Last thing before we actually go down this rabbit hole is the heap. So memory is allocated in into the computer. As you can see, it's all on that side. It's shared with the operating system. It's shared with the virtual machine. It's got the memory heaps of Ruby itself. So as memory is allocated, you take an entire heap slot. That heap slot is then divided into individual R-value-sized components. So that's where I store these objects. Those are the pointers to those objects themselves. When I run out of slots, when I run out of spaces on the heap itself, I can either put another heap slot together. I can run garbage collection to free stuff up. If I happen to fill up all of my heap slots and all of my memory is gone, I have a memory error. I'm out of memory. That's what happens. So GC is all about cleaning this stuff up so I don't run out of memory over time. I can either return information, I can return the available slots, or the available heaps to the VM, or I can create whole new ones. And we want to do this as little as possible, given the fact that it's really expensive. So, you guys ready for a rabbit hole? Because this is where it gets ugly. You thought you'd seen some C, and now it's time. So the very first thing that happens when you call Foo.new is this. This is what gets executed. RB class new instance. You're passing in the class, you're passing in some arguments, and what's happening is we're going to allocate the memory space. So that's the first thing that's going to happen. Then the initialize method of that class is going to get called, and then we're going to return the object. So that's pretty typical. You've seen that before. So what happens during allocation? So let's chase that down. We end up with the allocator. So we initialize an allocator, but like I said, our class, our string, our array, every kind of Ruby object has a different kind of allocation. It gets memory in a different way, because it needs to be tracked in different ways. So we need to find out what function is actually being called in order to allocate memory for a basic object, for our foo class. That's just a basic object. So now we need to go and find RB get alloc function. So we dig into there, and we see that inside of all this checking and whatnot, we end up finding that this member, this allocator off of this C macro, is where the allocator is being defined. So we just pop it off of there, and we end up getting our allocator function. But where in the world is this allocator member defined? So we have to do some hunting. We do some, C tags are your friend when you're using when you're looking at the source code. So make sure you have C tags installed. And we jump down, and we find that inside of RB define alloc function, we see that we pass in the class and the function itself that's being allocated. So you can see we set the allocator to a function, and then that's being passed in here. So now we need to chase down, where does a basic object get that defined? How do we tell basic objects or which functions are doing? So you do a little more digging. You end up in object.c, and that's in the init object. This is the object system being created in Ruby when it's getting compiled. So we can do a little bit of hunting. We find that basic object is passing in this function, RB class allocate instance. That is the function that's called when we want to allocate just basic memory for a basic object. Great. So let's keep digging. RB class allocate instance gets us a macro. It's macros all the way down. This macro is going to help us create objects and keep them inside of the memory space so that we can track what's been allocated, what hasn't been allocated, what's free, what's not. So we're going to dig down into this new obj of. And this is where I get a little busted. The title of the talk is down the RB new obj rabbit hole. Well, in fact, RB new obj never actually gets called. It's a deprecated function. RB new obj of is the thing that actually gets called these days. So this macro substitutes out to this. So we need to hunt that down. So we've got our class type and our flags that we're passing into it. And we move on to the next one. Now we're into the nitty-gritty, right? Now we're actually starting to allocate this object. So we're going to create a new object of this class. This is the world of dependency injection galore, where we just have passed this class down, I don't know, where are we, like 7 or 8 layers down now? And these flags, we keep passing them down. Eventually, we end up looking at new obj. Now, you can see this is a long function, so we're going to take it chunk by chunk. And this is where the magic happens. This is what is going to happen. So first, we need to get object space. We need to get the memory space that we can then put things into. We're going to jump past a bunch of error checking and reference checking, or just making sure we're sanity checks. Then we're going to go garbage collection. I'm going to hand wave here for a second and say, like, all right, well, garbage collection doesn't need to exist, doesn't need to happen, and or it happens successfully. Let's assume garbage collection just did its thing. So we keep on moving down. We end up popping off the free list of available from object space, right? Like this is the next space available, so we get a pointer to that next space. We put in a new space into the old space so that next time we want to create another object, the next one's available to us. We zero out that memory so that it doesn't contain anything in it, and then we increment the number of objects being allocated and then return that object. That happens 280,000 times when Ruby runs, when a Rails app boots up. I think that's pretty impressive for the performance characteristics of how much has to go on in order just to get an object created, 280,000 times. So I kind of hand waved for a second. And what's important about this is now we're going to start looking at how the garbage collector is going to change over time from 1.8 to 1.9 to 2 and 2.1, and how this is going to change the way we think about how Ruby is traditionally being, was originally designed, and then as Vicent kind of alluded to, it's different now, right? Rubinius and JRuby are of a different era, and I think MRI is certainly going in that direction, and the core team is certainly attacking that problem. I think they understand that problem. So let's get into some garbage collection. Garbage collection is actually pretty mundane when it comes down to it. It really is just 2 loops. There's a GC marks and a GC sweep. Those are just 2 while loops that go through the marking phase and the sweeping phase. And so those look like this, nothing really special. There's a bunch of marking that needs to be done on things that never get collected. Things like symbols never get collected. So in GC marks, we actually do a bunch of that stuff and then go to GC mark stack objects. And you can see it's just a while loop. That's just going to pop off an item, mark it, and keep going down until it gets through all its children. That's all it's doing. Once that finishes, we move on to GC sweep, which again is just a pretty mundane loop of take an object, sweep it if it's not marked, and then send it back and step repeat until you're done with all your objects. That's it. So that is object creation. So now let's get into garbage collection itself. So let's create a bunch of objects. Right? Here's our 10,000 foo objects again. Memory looks something like this, right? So we've got our root set, which is all of the things available that we've allocated, and then here's all the memory and their children, right? So there's a 10,000 foo objects kind of hanging out in the back. So what we want to do is take a look at the FL mark flag on the flags in RBasic, right? So you remember, like, we've got a heap, the object includes RBasic, you dive down into the flags, you can get FL mark. That tells us if an object has been marked. If the object hasn't been marked, when we get to, we're going to nil some stuff out. If the object hasn't been marked, right, we're going to remove it. So what happens is we've unlinked these so that those while loops that say, I'm going to start here and work my way in, stop at this point in time, right? So on this last one, that while loop never gets further to continue the marking phase. So it's going to start with this outer root, so foo. It's going to find that our class is still available. Then we're going to move on to each object and each of its children and mark them. We're going to change that flag every time that we can reach it from the root set. So it ends up looking like this. This is what our memory looks like right before the sweep phase happens. So we've marked everything. Now what we're going to do is sweep everything. What we're going to end up doing is assume the things that aren't marked are garbage and just and collect them. They're going to put them back in the free set. So then our memory ends up looking like this. So again, our mark and sweep phase is stop the world. So your code isn't happening every time an object gets created. It checks to see if it needs to do garbage collection. Sometimes it doesn't. Then it goes through its garbage collection process if it does, and then your code can continue executing. So you keep creating all these objects over and over and over, and at some point we need to run garbage collection. That's a very long process. The other problem with mark and sweep is that every object is touched at least once. Everything is touched once because it has to be swept, right? So what happens is during the sweep phase, if it had a mark on it, the sweeper has to remove that mark. And then if it didn't have a mark on it, like these things down here, it puts those back in the free set. So every object is touched at least once, and anything that gets a mark on it is touched twice. That's a long process. Doing this pointer traversal is really expensive. And if you think about your Ruby code, when you put Foo.new into a piece of code, that actually gets created into memory, and that's stored in memory. So every time that exists, any chunk of Rails, the hundreds of thousands of lines of Rails, go into memory, and they run through this. They have to run through this mark phase every single time. And that can get really expensive to keep marking these things and unmarking them, marking and unmarking. And you do this over and over and over. So, as I said, your mutator, your code, stops running. Stops running when this garbage collection is going on. So this gets us up to 1.8. This is how 1.8's naive, what I'll call a naive mark and sweep garbage collector ends up getting us. So how can we mitigate some of these problems? So we can do lazy sweep. Lazy sweeping is that we don't run garbage collection every time an object's created. We actually see if we need to run garbage collection. So we see, is there enough memory available? If there is, then go ahead and use it. When it's a more advanced lazy sweep is when it runs only long enough to free up enough memory space to allocate the new objects it's trying to create. So that's good. But lazy sweep's a misnomer because it's not the sweeping phase that's the hard part. It's the marking phase. So we still have to do this marking all the time. And we want to kind of skip the sweeping phase. So we don't get that far with lazy sweep. It's just postponing the problem. So we need to start exposing this differently. So Unix has a concept of copy on write. So I'm assuming many of you use Unicorn. So it forks a process, and it has shared memory at that point in time. Sounds like a good idea, right? Because you can fork your process, you've got all the shared memory, you're not dealing with it. There's a problem with copy on write in Ruby, though. And it has to do with the data structure that all of this, the FL mark flag exists. So if we have two processes, if we have process A, and then we fork it, and we have process B, they each have their own memory set, right? They have heap A and heap B. And anything that was shared amongst them when process B was forked, you end up having this shared memory set. So this might be your Rails code is shared for a long period of time. But once one of these processes changes the contents, right, whether it's a value or whatever, it's no longer shared. So the problem happens during the first mark phase. So process A runs its garbage collector, and it will garbage collect everything it has memory access to. So it's got access to heap A and shared memory as well. So it marks all those things. But we've just changed everything that's in shared memory. We've marked it, and we've changed that flag. So now there's technically nothing that is shared memory anymore. So that doesn't get us anywhere. So In Ruby 2, where we get a lot of these performance increases, is from the change of the data structure that this mark is stored. We move to something called bitmap marking. Bitmap marking puts a bitmap at the top of the heap telling us whether something is marked or not. So no longer is the flag changing, it's this header inside of the heap. And now that's really important, because now copy and write works. That's where you're going to get major performance improvements out of something like Unicorn with a forking process. You can take advantage of Unix's copy and write fundamentals and really see some performance increase. So, as I'm running a little long, now what? So, as I said, I think MRI got a bad rap as being slow. But tons of work has been done on the garbage collector, both from the naive market sweep that was kind of found its way up to 1.8, to lazy sweep, which is an improvement, to bitmap marking, which was another major improvement. And then now we're moving into generational garbage collectors. There's a great talk from Baruco, from Koichi, that actually goes over his plan for this, and Matt's talked a little bit about it. So generational garbage collector splits your memory into two chunks, stuff that is old and stuff that is new. So your Rails code will end up in old memory. So it won't go through that marking phase nearly as often. That's really important. So then we're only killing new objects as they get changed. And I think there's really something to be said about that. So I think Vicente is very smart. I think Rubinius is a great project. I think JRuby is a great project. I don't think all hope is lost when it comes to MRI, at least on the garbage collector front. Now, the GIL and all of those things, I'm not going to get into those concepts, and that's another area to complain about. And the C extensions, and that's a whole other thing to complain about. But when it comes to performance characteristics based upon the garbage collector itself, we've seen major improvements. And 2.1 is an even more major improvement because of this generational garbage collector. It's really smart, and all of this stuff was done through C macros. I think it's really important that we also start to contribute to it, that we start to get involved in the conversation rather than just complaining about it. That's the nature of open source, is that we can contribute to it. And I think that's something that we sometimes forget. So I wanted to give you some places to start. So if you aren't familiar with C, if you aren't familiar with where to sort of do this research, because a lot of it is translated Japanese, here are some places to start. First, you've got this uniprocessor GC techniques paper. It's a great, and these slides will go up online so you can get them all off of there if you'd like. It's a great paper on garbage collector techniques in general. Then I think it's really important to read Rare RGC Talks. That gives you an overview of how the GC works overall. The Garbage Collector Handbook, if you're interested in how things like generational garbage collectors are working, how parallel garbage collectors, like Rubinius is working on a different kind of garbage collector that runs in line so that it's not stop the world anymore. Those kinds of algorithms are talked about in there. Again, Ruby Hacker's Guide is really important, and Pat Shaughnessy's amazing Ruby Under the Microscope. These are two great sources for how to learn the C that goes under Ruby and how you can contribute to that. And then lastly, if you're not familiar with C at all, I think the C programming language book, the very classic, is a good place to start. I don't necessarily think Zed Shaw's intro to C is appropriate for the Ruby C that you're going to be looking at. So I would actually recommend the C programming language instead. So thank you very much.
That was more C than that was awesome.
Too much C?
I went in there and I saw some C from the side, and I thought, no, nothing wrong with C. All right, the men with the microphones. I say that purely because A, they're men, and B, it's alliteration, which is awesome. I mean, it's my language. I can play with it. Questions?
Okay, so it's not really a question, but it's more of a statement.
I don't want to stop you, Jamie,
Shut
but this
it.
is question and answer time.
It's statement and statement time.
I'm going to sit in the middle. So I'm just feeling really confused now, because we started off with one guy who said, oh, Ruby sucks, and then you're saying, no, it doesn't suck. And another guy who wrote it, who says, no, it definitely doesn't suck, it's awesome. 2.1, so what is it? Is it the garbage collector that's okay, but then everything What sucks?
So depending on who you ask, right? Like, a lot of the performance problems some of the performance problems start with the garbage collector, right? 1.8 was slow because of this naive mark and sweep, but it's also the GIL that's a problem. So you can't do things like concurrency. So some people think concurrency is the end-all, be-all to performant applications, and that's not necessarily true. Parallelism, for example, could be a different solution. Forking, if you don't want to have to deal with thread safety and concurrency, then use forking processes. But up until 1.9, when the copy on write stuff got in, you couldn't use copy on write, so that didn't do you any good. So everybody's going to have a different take on performance problems in Ruby. Some people are going to think concurrency is the solution. Some people are going to think like improved garbage collection is going to be the solution. I actually don't think Percent was saying that it sucks. I think there are barriers, and the C extensions are unfortunately so far gone that at some point we need, at very least, need a breaking change. Something that says, all right, everything after this is screwed, and we need some way to designate that. I think everybody here thinks Ruby is awesome. It's just the implementations can be challenging, and I think that's important to distinguish.
Okay, so I was being a little bit rude by saying it sucks, but I guess, so what you're saying is that there are certain bits that are better in certain different situations.
Yes.
It would be nice if someone could just outline what situations we should be using what in.
I mean, I was listening, and I don't mean to call you out.
But
you did introduce it. You said that Ruby was built not to do the long-running things that we now sort of expect of it. And I mean, I think that's where the challenge comes from. I mean, I'm just the MC.
I can't speak authoritatively for the Ruby core team. I am not on the core team. I've only had the privilege of meeting Matt a handful of times and chatting with him, and Koichi a handful of times. But I do think Ruby has changed what we're using it for, right? Like, this was a programming language written in 1993. The world is different today. We do different things 20 years on. So the language needs to evolve, and that's what's going on. I think there's that evolution, and there are certain, again, part of it has to do with restrictions on time. There's only a handful of people that are contributing to Ruby core. Tons of people contribute to Rails. Not nearly as many people contribute to Ruby core, but there's 600 people sitting in this room that use it every day. And part of my goal is to help at least alleviate some of that stress or some of that barrier for entry, and maybe it will spark your interest in contributing back to Ruby core. And then we can get things like, maybe at some point the GIL can kind of come out, right? I don't think it's possible. Matt's is the final say on that, but at least we have other people contributing to it rather than this backlog of changes that we have to, like, both as a feature set of the language, adding things like, say, refinements. They're doing that and not doing performance characteristics. So maybe there's some people that want to work on performance that while the core team is working on other components. So I think that's maybe answers your question.
Oh, well, I think I can summarize with that your next talk should be on, what you can use in certain situations depending on what you need. That'd be great.
Sure.
Use 2 and this if you want this. If you want that and that, use this and this and that.
It's a good idea. I'm retiring this talk. This is the last time I'm giving it.
I'll come to your next one then.
Awesome. Thanks.
Hi. From the point of view, you talked about parallelism right now. Is that an approach that has been studied for Ruby? Is that not viable? Or is there room for experiments in that field?
Sure. Rubinius, for example, is working on concurrency. MRI can certainly work on, you can use processes, you can run Ruby in a parallel way where you're not having to worry about this thread safety and all of the sort of nuances that come with that. So you get the GIL in each of your processes, and you just can serve more requests that way. So I don't know if there's a ton of experimentation other than where the thresholds that, maybe to answer the previous question, where are the thresholds that end up being a good use case for something like a forking web server versus doing a concurrent system? Those are sort of advanced topics that every application is going to be written differently and needs to be kind of experimented with individually, right? And it's going to change. Your application will change over time. When you first write your code, and then 3 years later when that application is still running, or that's whatever you're using, whatever you've written it for is still running, the load on it, the functions it's doing, is all going to change. So you need to kind of always be adaptable and not think that the thing you started with is the thing you need to end with. So I don't know if that really answers your question.
I was asking more in the terms of, is there room to explore it in the Ruby source code? Are there, you talked just in the previous answer, you spoke about exploring parallelism in the way of improving the language performance. I was asking more in
Oh, are there like hooks and areas that you can focus on?
Yes,
I don't know. I don't think I've come across any. I don't think there's been a ton of work done on that, but it's something that is certainly worth looking into. And since Mats is here, I would definitely sit down and talk with him for a few minutes about where can I contribute, where can I kind of dig in, where's the place to do that. So I don't know where parallelism might fit into that scheme. I haven't run across anything that's being done right now.
Okay, thank you.
Yeah. It's intimidating, this one.
Okay, the main question, how this new garbage collector stable? Is it tested on huge Rails application, for example?
I don't know. Are you running trunk? Because 2.1 isn't out yet. So the generational is in 2.1 currently. And so does anyone run sort of edge Ruby in production, right?
Okay, then
I'm going to take that as a no.
then another question, how these new releases of Ruby, which one will be stable and which one will be experimental?
That's more of a question for release management of Ruby, but right now 2.1 has the generational garbage collector. I have run applications on it. I haven't done a big application in it. I'm sure it hasn't been tested with all of the C extensions and all of that. There are massive numbers of hooks and checks that go into the generational work that Koichi did, and you can actually just turn it off straight away. So there's a config flag that you can turn off generational, and it'll never run, and it'll never try when you compile Ruby 2.1. So if you do run into a problem, there's an automatic out. If you dig into the gc.c file in 2.1 or on trunk right now, you're going to end up seeing massive references to this restricted gen GC. So, but unfortunately, Ruby doesn't have a way to test. Like, there's no standard application in which we can test a new Ruby against, right? Like, nobody has ever written a system which says, like, here's a bunch of sort of stress tests and smoke tests for Ruby itself. Let's see what breaks, and here's all the thousands of C extensions that people like you and me have written, maybe poorly 10 years ago, and those break, right? Like, that's the problem, is that we don't have that. If somebody wants to take on that challenge, you're welcome to. I don't envy you. What was that? Yeah, and it'd be interesting to see.
Normally they just take
ask the
a
question
huge
again,
Rails
sorry.
application and run it like 1,100 times. And
But so a complex application, if we're talking about Rails, there are multiple code paths in which that code can run through. There's only certain edge cases, right? We try to cover our application with tests, but catching every edge case and every code path that is going to be executed is really hard. So you might not, until you do something like GitHub did, where it ended up just finding these bugs over time because of stress, you're just not going to be able to find. That's a really difficult problem, is to be able to cover all the code paths and doing static analysis against a Ruby, and it's no longer a static analysis because you're executing the code against a VM at the same time, right? So that's a challenge. That's a meaningful challenge that I don't think I could undertake.
I mean, you might want to run increasingly portions of your app on the new Ruby in parallel, have some traffic.
Yeah.
If it's a web app, have some traffic go through it. That way, at least you can fall back if it's not good, or it can increase more if it is turn out to be good. Does the new Ruby, can you currently use it through the Heroku Cloud Foundry build packs?
I couldn't tell you.
Couldn't tell.
Probably not, but I think Terrence
I haven't looked at it. Yeah, Terrence's problem.
Terrence isn't here this shockingly at a Ruby conference, but I don't think you can run 2.1 with its currently Edge. It's not officially a release.
Hello?
Oh, someone from Heroku can answer that question.
Actually, I have no idea.
Richard, right.
I'm sorry.
But I did have a comment on the last question. Something that helps us a lot at Heroku is Travis. So
No, stand up, short person. It's Richard, by the way, who works at Heroku.
He'll speak later.
Yes, I will speak later. We flag, so Travis allows you to flag your own personal Rails project into testing against Ruby head, and you can even flag it and say, like, I don't even care if this fails, but that way you'll know. And like, if you start seeing failures, maybe come like November, when it's getting a little closer to release time, like you can actually report those bugs, if there are any, to back to the core team and help them out.
That's awesome. So that's a way to get distributed number of applications trying it out.
Richard, so just to clarify, from Heroku build pack perspective, only when it comes out will it become available in the build pack? Like there's no way of using Ruby head in the bundle in the gem file?
I think you can. It's just whether or not so we have to compile it, and it's an issue of how frequently are we going to compile it, and like.
Fair enough. Yep.
You know what, you wouldn't even be getting the same version. So, yeah. But when it comes out on day 0, it'll be available.
Christmas.
So I want to ask you, as I understand that generational garbage collector, it's scoping collector, so it moves the memory out. And about some C extensions, there of course can be some problems in this. How the Ruby team will handle this? Because I didn't find this information everywhere.
Yeah. So the generational only affects things that are gone through the actual, like using all of those macros. It then keeps a whole list and puts only things that it's gone through that system into the old. Everything else is considered new. So if there's a writer of a C extension that aren't using the conventions or are using the pointers directly, that is always considered new. And so it'll always get marked, and it'll always potentially get swept if it's no longer in use. It's only stuff that has gone through the new generational garbage collector system that ever gets marked as old, and so it will only get lapsed at that point in time. So that's how Koichi got around it.
But the generation garbage collector, it reorganizes memory with generation, so not to fragment the generation. It moves it anyway, or in this implementation it wouldn't be.
So in this implementation, it's strictly using sets to keep track of everything. It's not actually moving memory around. And I think Rubinius does the same thing, where they're not. It's how often it gets marked is the part. That's why it's the restricted generational. So it's only keeping track of which stuff is old and new. It doesn't actually move it in memory because it doesn't need to. So it's just a matter of how often does this mark phase go on. And that's theoretically one of the expensive components of the GC in general is the mark phase. So Matt said that it's saving about 50% on that mark phase. So it doesn't actually move memory.
To your left.
Hi. So this garbage collection thing is essentially this massive black box, which we don't really see a lot into. I mean, obviously, like New Relic, you can see kind of the time that is spent in there. Are there any other kind of tips for trying to find out what part of your app is causing problems with the garbage collector, aside from just putting logging like all the time how many objects you're using, etc.?
Aaron put in a ton of dtrace probes around performance stuff not too long ago. So you can use dtrace to kind of do some inspection there. Unfortunately, writing your application in a different way that doesn't affect garbage collector is sort of an edge case. Not a ton of applications go that direction. So this isn't a like, hey, here's how to evaluate your Ruby app and then make these major changes to how you write Ruby code. This is the reality of what Ruby does and how we can change Ruby itself. So that's the difference. There's very small, I've heard some people saying, well, they'll stop garbage collector at a certain point and then restart it manually. But I've only heard that every 10,000 apps or something. So it's unlikely that you can write your application meaningfully differently to save yourself from the garbage collector every now and again.
And is dtrace something that you could run in production, or is it more like a development tool?
So I think there are people that run dtrace in production. You can you can connect to it and find out what's going on in it. So I don't know how many people run it. How many people are familiar with dtrace, I guess, is a good question. So yeah, it's not a popular tool in the Ruby community yet. It's I asked Aaron like, where's a good like dtrace tutorial, and he's like, a lot of Googling. So yeah.
All right, please put your hands together for Chris Kelly.